Hello friends, today I will discuss the sources, source conversions, Kirchhoff's voltage law, Kirchhoff's current law, voltage and current relations in resistor, inductor and capacitor. And also I discuss the resistors connected in series, resistors connected in parallel. Similarly, when the inductors are connected in series, when the inductors are connected in parallel, when capacitors are connected in series, in parallel, and also the vector diagrams when the resistors and inductors are connected in series, when resistor and capacitor are connected in series, and all combinations will be considered with fixed values of R, L and C, and later I will discuss the locus diagram keeping one element like resistor varying in a RL circuit or R fixed, L varying like this. All combinations will be discussed at the end. AC circuit with parallel branches will be considered for drawing the locus diagrams. Let us consider first what are the basic elements in the circuit theory. There are two types of elements. One is called the active elements, the other is called the passive elements. Passive elements are resistors, inductors, and capacitors. These passive elements cannot generate any power. Next, coming to the active elements, they come and like voltage sources, current sources. Again, these sources are divided into two parts. One is called dependent voltage sources, the other is independent sources. So let me consider first independent sources. Under independent sources, we find two categories, voltage sources and current sources. Again, under voltage sources, we find ideal voltage source, that is DC. The other is practical DC voltage source. Similarly, under current sources, we find the ideal current source, that is ideal DC current source. The other is called practical DC current source. Let me consider first what is the representation of the ideal voltage source. So this is the representation of ideal voltage source like this. So its polarity do not change with respect to the time. And this same thing we can also represent like this. This also can be represented like this. This also can be represented like this. We can also represent like this if it is a AC voltage source. And all this comes under the category called ideal voltage sources. Their internal resistance is 0. And coming to the independent current sources, the representation for the independent current source is like this. This is the ideal current source. For this, the internal resistance is infinite. Let us see what is ideal voltage source characteristic, VI characteristic. As we have seen, ideal voltage source representation is like this. So if it is connected between terminals in AB and load is connected across this AB, and if the voltage is if the load is varied, then the load current varies. When the load current increases, in this case, the voltage across the load do not change irrespective of the time. So it is called the ideal voltage source. So that is the reason here for all time at any load current on x-axis, the load terminal voltage, that is AB, VAB, is constant from here to here. Coming to the practical voltage source. A practical voltage source will have the internal resistance R, and this value will be very low, but it is not equal to 0. So under this condition, when the load is connected between AB terminals, when the load is varied, load current also varies. Once the load current increases, automatically the voltage across this small resistor R increases. As a result, the available voltage across the load will be the, the source voltage minus the voltage drop across this will be available. So this voltage across the load decreases with increasing load current like this. So that is the reason why the voltage source of practical case will have the characteristic like this. Next, current source. As we have seen, the current source representation is like this. Its internal resistance is infinite, and when we draw the characteristic between current output and the voltage across the load or time, then we get like this. Irrespective of the load voltage and time, the current supplied by the current source, ideal current source, is constant like this. That is parallel to the x-axis, that is parallel to the load terminal voltage. When it comes to the practical current source, it will have the resistance, but it is not infinite. It will have a some value which is less than infinitive. Still, the value of R is very high. So the current taken by this resistor under different load conditions will vary. So when the load current increases, automatically that part of the current will flow here in this. As a result, the available current across the load decreases. This is the load terminal voltage, and whereas this is the current flowing in the load like this. So initially it is here ideal value. As the load current changes, automatically the current flowing in this flows. So as a result, the available load current varies like this, means decreases. So this is the practical current source VI characteristic. Now let us see dependent current source, dependent voltage sources. This is the dependent voltage source representation. So it is in the diamond shape. Within the diamond shape, we find here plus sign, here minus sign here. Similarly, its value depends upon gain in some of the branches in the circuit. Coming to the dependent current source, this is also in the shape of diamond like this. Within the diamond shape, we find a arrow like this, which represents the current direction of the dependent current source, and this value also depends upon the gain or the values in the other branches of the circuit. Coming to the classification of the dependent voltage sources, there are two types of dependent voltage sources available. They are called the voltage controlled voltage source, which is normally represented as VCVS, and the symbol will be like this. This is the dependent voltage source, or voltage dependent or voltage controlled voltage source. The magnitude of this dependent voltage source depends upon the voltage across these two terminals, that is V1 here, and mu is the gain of this voltage source. So similarly, there is another type of dependent voltage source that is called current controlled voltage source. This is the dependent voltage source and its value is represented as R into I1, and this I1 is the current flowing in the neighboring circuit like this, and R is a constant. So the magnitude of this voltage source depends upon this I1 and also this R. So that's why it is called current controlled voltage source. Similarly, we find current sources which depends on one on voltage, the other on current. So let us see voltage controlled current source. This is represented as VCCS. So here, this is the dependent current source G into V1. Its magnitude is G into V1, and this V1 is the voltage across in the neighboring circuit, that is here V1. So this value, its value depends upon this voltage and also a constant called G, and its direction is downwards here. Similarly, there is another current source, that is current controlled current source, normally written as CCCS. So this is the representation of the dependent current source and the direction is downwards and its magnitude is depends upon beta into I1. Beta is a constant value and I1 is the current flowing in the neighboring circuit like this. So its value depends upon beta into I1. So let us see how to control or convert a practical voltage source into a practical current source and vice versa. So let us take, this is the practical voltage source, independent voltage source representation. This is V and this is the internal resistance small r, and if we want to convert this into equivalent current source, divide this V with its internal resistance, then we say that is the current source magnitude called I. I is equal to V by R, and in parallel with that, put this resistance across the current source like this. Suppose we know the practical current source and wanted to convert that to practical voltage source. So this is the current source, practical current source, so whose magnitude is I, internal resistance is small r. When we want to convert that to voltage source, equivalent voltage source, multiply this I with R, then we get that a new voltage source, that is V is equal to I into R. We put this resistance in series with the voltage source, that is like this. Let us see when the resistors are connected in series and when they are connected in parallel. So let us see first series resistors. So this is the applied voltage called V and connected in series with three resistors R1, R2, R3. Then the current flowing in this can be calculated as V divided by R1 plus R2 plus R3. So we can also write KVL equation, that is voltage rises equal to the voltage drops, that is V is equal to IR1 plus IR2 plus IR3. So this V, let us say, is replaced with the current flowing I into a resistance called R equivalent. Then substitute this in this equation. Then we get I into R equivalent is equal to I into R1 plus R2 plus R3. So from this we can write R equivalent is equal to R1 plus R2 plus R3. If R1 is equal to R2 is equal to R3 is equal to R, then the R equivalent will become R plus R plus R plus R, that is 3R. Then the R equivalent we can write simply 3R. Suppose the n number of equal resistors are connected in series. In that case, so write that n number of resistors number here, then multiply with the resistor available, that is n into R. Similarly, when the resistors are connected in parallel like this, here R1, R2, R3 are connected in parallel to the supply called V. Then this supply supplies the current, total current I, and this branches R1 receives current I1, R2 receives I2, R3 receives I3. And we can write the KCL at this node, that is I is equal, that is input current is equal to sum of the leaving currents, that is I1 plus I2 plus I3. And let us say this small I, that is total current, we can represent as supply voltage V divided by R equivalent, that is using the Ohm's law. Then we can also calculate I1 as V by R1, I2 is V by R2, I3 is V by R3. Then substitute all those values in this equation, then we get V by R equivalent is equal to V by R1 plus V by R2 plus V by R3. Then this V going to get cancelled, then we get 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Suppose R1, R2, R3 are equal to R. So in that case, 1 by R equivalent will become 1 by R plus 1 by R plus 1 by R, that is 3 by R. So once we calculate R equivalent, we get R by 3. So here there are 3 resistors, equal resistors connected in parallel. So we write here the resistance given by the number of resistors. Suppose the n number of resistors which are equal connected in parallel, in that case R equivalent we can write as simply that R divided by number of resistors n. Similarly, suppose we have the inductors connected in series like this. So let us say this is the supply AC voltage connected to the three inductors L1, L2, L3 which are connected in series. And the current flows here, that current we call as I. And we know for an inductor the induced voltage, the voltage across individual inductor is L into di by dt. Because since here the same current flows but varies with time, so we can write the KVL equation for this, that is V is equal to L1 di by dt plus L2 di by dt plus L3 di by dt. Suppose we write the net voltage applied is equal to L equivalent into di by dt, then we can put in this equation, then we get L equivalent into di by dt is equal to L1 di by dt plus L2 di by dt plus L3 di by dt. Because the rate of change of current is same throughout the equation, that will cancel, then we get L equivalent is equal to L1 plus L2 plus L3. Suppose the inductors L1 is equal to L2 is equal to L3 is equal to L, then the equivalent inductance will become L plus L plus L is equal to 3L. Then we can say L equivalent is equal to N into L if the n number of inductors are connected and which are same in value. So let us see, suppose inductors are connected in parallel like this. L1, L2, L3 are connected in parallel with the supply voltage V, and the voltage is AC voltage. So then we already know that when the current drawn by the inductors is time varying, then we can say the voltage across inductor is given by formula called L into di by dt. So from that we can write like L into di is equal to V into dt. So then from that we can write di is equal to V by L dt. So if we integrate this, then we get integral di is equal to 1 by L integral V dt. Then we can write I is equal to 1 by L integral V dt. Suppose the equivalent inductance is L equivalent, then we can write I equation, that is total current equation, as like this. I is equal to 1 by L equivalent integral V dt. So writing the KCL equation for this, note, we get I is equal to I1 plus I2 plus I3. Then we know what is I, that is 1 by L equivalent integral V dt is equal to 1 by L1, that is in place of I1, we write 1 by L1 integral V dt. In place of I2, we write 1 plus 1 by L2 integral V dt, plus in place of I3, we write 1 by L3 integral V dt. So these I1, I2, I3 are the currents flowing in the inductors L1, L2, L3, which are in parallel. And if you look at this, the same voltage is available across each inductor. It is varying in nature. So if you look at this equation, so both the sides, the integral V dt going to get cancelled. Then we get 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3. If L1 is equal to L2 is equal to L3 is equal to L, then we can write 1 by L equivalent is equal to 1 by L plus 1 by L plus 1 by L, that is equal to 3 by L. So we can write so 1 by L equivalent is nothing but 3 by L. So L equivalent will become L by 3. So here there are 3 inductors, each having L value is given by L by 3. If there are 4 inductors, in that case L by 4, it will become L equivalent L by 4. If there are n equal inductors connected in parallel, in that case L equivalent will become L by n. Let us see when the capacitors are connected in series. We know in a capacitor, the charge stored in the capacitor is given by Q is equal to C into V. So we also know the current is nothing but rate of change of charge, that is dq by dt. So we can differentiate this Q is equal to CV, and here the applied voltage is AC voltage, which varies with the time. So when we differentiate it, we get dq by dt is equal to C into dV by dt. C is a constant value. So this dq by dt can be written as I. So is equal to C into dV by dt. So from this we can write I by C into dt is equal to dV, or in other words, we can take the integral both the sides, that is integral dV is equal to integral I by C dt, or is equal to 1 by C integral I dt, or we can also write as V is equal to 1 by C integral I into dt. So if you look at these capacitors, the voltage across capacitor C1, we say V1, the voltage across C2 as V2, voltage across C3 is V3. So in that case, applying the KVL to this loop, we can write as applied voltage V is equal to voltage drops, that is V is equal to V1 plus V2 plus V3. And we know the voltage across in each capacitor can be written as V is equal to 1 by C integral I dt. So here also we use the same formula, that is for net voltage applied, we can also write like this: V is equal to 1 by C equivalent integral I dt. Whereas for V1 we can write 1 by C1 integral I dt For V2 we can write 1 by C2 integral I dt. Next for C3 we can write 1 by C3 integral I dt. So once we substitute this in this for this in this equation, then we get 1 by C equivalent integral I dt, that is in place of this we are writing like this, then is equal to, and we write here in place of v1 v2 v3 this, and we take the integral I dt as common, then we get 1 by c1 plus 1 by c2 plus 1 by c3 like this. If you look at this, this is a series circuit and current integral is same, so current is same, so this integral I dt going to get cancelled from left side and right side, then we get 1 by C equivalent is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Suppose the capacitor values are same, that is C1 is equal to C2 is equal to C3 is equal to C. In that case, we get 1 by C equivalent is equal to 1 by C plus 1 by C plus 1 by C is equal to 3 by C. Then we get C equivalent is equal to C by 3. Suppose n number of capacitors are connected in series. In that case, if the capacitor values are same, in that case we can write C equivalent is equal to C by n. So when the capacitors are connected in parallel like this across a AC supply like this. So here V is connected in parallel with C1, C1 in parallel with C2, C2 in parallel with C3. So each capacitor will draw its own current. Here it is I1, here C2 receives I2, C3 receives I3, and the total current supplied by the voltage source is small I like this. And we know in a capacitor Q is equal to CV, and that we can also say dq by dt is equal to C into dV by dt, that is current is equal to C into dV by dt. And applying the KCL at this node, then we say the input current at this node is I is equal to I1 plus I2 plus I3. This I1, I2, I3 are the current leaving from this node. So this is the input current, these are the outgoing currents. So then in place of I, we can write C equivalent into dV by dt. And whereas in case of I1, we write C1 into dV by dt. For I2, we write plus C2 dV by dt. For I3, we write plus C3 into dV by dt. So because it is a parallel circuit, the variation of voltage is same across each element. So that dV by dt going to get cancelled both right hand side and left hand side. So we end up with C equivalent is equal to C1 plus C2 plus C3. Then C1 is equal to, if this C1 and C2, C3 are equal and that two value is C, in that case we get C equivalent is equal to C plus C plus C plus, this is 3C. Then C equivalent will become 3 into C. Suppose n number of equal capacitors are connected in parallel. In that case, the equivalent capacitance will become N into C. Now let us see the voltage and current relations in a resistor. Suppose AC voltage is connected to a series resistor like this. Then the current flowing in this circuit is small I. And let us say the applied voltage AC is given by V is equal to Vm sin omega t. So let us say this is equation 1. And then using the Ohm's law, we can calculate I is equal to applied voltage V divided by R. That is equal to V is nothing but Vm sin omega t. And divide that with R. Then we can replace this Vm by R as maximum current flowing in the circuit, that is Im. So then we can write I is equal to Im sin omega t, this second equation. So if you look at this equations 1 and 2, there is no phase difference between these two equations. So the voltage and current are in phase with each other. That is like this. This is the applied voltage or the voltage across the resistor, and this is the current flowing I, which is in phase with this voltage vector. And this we can also draw vector diagram like this. This is the V, and in phase with that is I like this. So if we represent that in phasor form, so this is the voltage waveform, sine wave. Similarly, there is a current waveform, so which also starts at the same as that of the applied voltage, the voltage across the resistor. That is, both V and I starts at 0 and also reaches their maximum here, and then again reaches their 0. It continues like that. And the phase angle between this voltage and current is 0, so the power factor for this is cos 0, that is unity. Similarly, we can also calculate or find what is the voltage relation between voltage and current in an inductor. So this is the inductor L connected to a AC source V. Then the current flowing here is I. Let us assume the current flowing in the circuit is Im sin omega t. And for an inductor, the inductive reactance is represented as XL, or simply X is equal to omega L, or that is also can be written as 2 pi FL. Then we also know for a pure inductor, the voltage induced across the inductor is nothing but L into di by dt. And here the current flowing is I. And if you write the KVL equation for this, the applied voltage or the induced voltage in the inductor is equal to V is equal to VL is equal to L into di by dt. So VL is equal to L into d by dt. I value we write like this, Im sin omega t. Then once we differentiate it, we get Im omega into L into cos omega t. So we know what is omega L, that is defined as XL, or X also we can write. And we can also write cos omega t as sin omega t plus 90 degrees. So writing that in this equation, then we get VL is equal to Im into XL sin omega t plus 90 degrees. Then we can also write this Im into XL as Vm, so that we get voltage equation VL is equal to Vm sin omega t plus 90 degrees. So if you observe this current equation and voltage equation, there is a phase difference 90 degrees, but the wave shape is same, that is sine. And this indicates voltage leads the current by 90 degrees. So vectors always rotate in the anti-clockwise direction, and voltage will have the y position, and whereas I is lags the voltage by 90 degrees like this, and thus 90 degrees we say phase angle, that is phi, as 90 degrees. If we draw that in the waveform or phasor form, we get like this. First voltage waveform will start after 90 degrees, I will start like this. The power factor for this circuit is cos phi, that is cos 90, that is nothing but 0. We say 0 power factor lagging for this circuit. So let us see voltage and current relation in a capacitor. So let us say capacitor is connected in series with a AC source like this. Then the current flowing in the circuit is small I. Let us say the voltage applied is nothing but Vm sin omega t. We say that is equation 1. And let us say the capacitive reactance, which is normally represented as Xc is equal to 1 by omega c, or 1 by 2 pi Fc. And then we also know for a capacitor, current flowing is given by I is equal to C into dV by dt, and we know what is V here, that is applied voltage, that is C into d by dt of Vm sin omega t. So once we differentiate it, we get I into C omega into Vm into cos omega t. And we also can write this cos omega t in terms of sine like this, sine omega t plus 90 degrees. And we can also write this Vm into omega c as like this, Vm by 1 by omega c. This 1 by omega c we can replace as xc. So then we write Vm by xc into sine omega t plus 90 degrees. And this Vm by xc we can say that is the maximum current that flows. So we can write as Im into sine omega t plus 90 degrees. This is second equation. This is first equation. And if you look at this, the waveforms are same, but current I is leading the voltage vector by 90 degrees. So if you draw the vector diagram and the vectors rotate always in the anti-clockwise direction. So I is here, I leads the voltage by 90 degrees and that phase angle is represented by phi and value is 90 degrees. And the power factor for this, we say cos phi is equal to cos 90 degrees. Then the value becomes 0, but we call this as 0 power factor leading. And if you draw this vector diagram in the form of phasor diagram, we see here current phasor starts first, and whereas voltage phasor starts at 90 degrees later. Now let us see in a AC circuit what is meant by impedance triangle, what is meant by voltage triangle, what is meant by power triangle. So let us say we have the R L circuit connected to a AC source like this. So here V is connected in series with L and R, and let us say the current flowing here is I. Then the impedance for this we write as the impedance of inductance, that is normally represented as J into XL or J into X, whereas X is nothing but 2 pi FL or omega L, and R is a resistor, so Z is impedance, so Z is represented as Z is equal to resistance R plus JX. So this is, we can write on a vector diagram like this. On x-axis we put R, whereas the inductive reactance X we represent on y-axis like this. It's a positive value, so we put it on positive y. And J represents, it is 90 degrees leading the resistor value. That's why we put here J. The importance of J is when it multiplies any quantity, that quantity moves by 90 degrees from its present position. So since we have the resistor here, inductive reactance here, the resultant of that is called the Z, that is impedance, and representing all this, that is R, X, on a single vector diagram is called the impedance diagram or impedance triangle. Suppose we multiply each vector here with current flowing I, then we get what is called the voltage across the inductor here, whereas here we get the voltage across the resistor represented by VR, whereas here voltage across inductor represented by VL, and the resultant of this voltage VR and VL is nothing but applied voltage V, which comes because of the KVL. Algebraic sum of the voltages across a loop is equal to 0, or the sum of the voltage rises is equal to the sum of the voltage drops. So it is written, that can be shown as vector diagram like this. The angle between this applied voltage and the VR is called the phase angle or power factor angle. Similarly, in the impedance triangle also, the angle between Z and the R vector is called the phase angle, that is power factor angle. Suppose each vector in the voltage vector diagram is multiplied with current flowing I, then we get what is called the power triangle. So VR multiplied by I will give the real power, whereas VL multiplied by I gives the reactive power Q, whereas V multiplied by S will give the apparent power. So representing the real power and the reactive power and the apparent power on a single vector diagram is called the power triangle. The phase angle between the apparent power S and the real power P is called the phi. Similarly, representation of voltage across the resistor and the inductor on single vector diagram is called the voltage triangle. This V represents the applied voltage. Coming to the units of the P, it's called real power, and units are watts, whereas Q is called the reactive power. Its units are volt ampere reactive, whereas the S, that is apparent power, units are volt amperes. So if you know these triangles, we can calculate what is the power factor of the circuit, that is cos phi is equal to R by Z from the impedance triangle, whereas from the voltage triangle we can calculate cos phi is equal to VR by V. So let us take a AC circuit like this. This is the AC voltage 100 root 2 volts connected to a series circuit 1 ohm and J1 ohm inductor which are in series. Then for this circuit, the first step is calculate what is the impedance, that is Z is equal to R plus JXL. So that JXL is given as J1, so whereas R is given as 1 ohm, so Z will become 1 plus J1 ohm. So once we know the impedance and the applied voltage, then we can calculate what is the current flowing here, that is I is equal to V by Z, that is 100 root 2 divided by 1 plus J1. So then we get here 100 root 2 divided by root 2, then we get 100 amperes. This is the current supplied by this AC source. And we can calculate what is the voltage drop across the resistor I into R, that is 100 into 1, that is 100 volts. Similarly, inductor voltage drop is nothing but I into XL, that is 100 into 1, that is 100 volts. And we can represent all this in the impedance triangle, voltage triangle like this. So this is the impedance triangle. R is represented as 1 ohm, and whereas XL is represented as J1 here, and the resultant is written as Z, that is 1 plus J1, that is root 2. Similarly, the voltage across the resistor and the inductor we can write as this VR into VR on x-axis, VL is on y-axis, resultant is applied voltage V. And we can also represent this in the power triangle as PQS. So we can also write VI vector diagram for this like this. So because it is a series circuit, take I as common. And in a pure resistor, the voltage across resistor and the current flowing, they are in phase with each other. So we say VR is in phase with current I like this. And whereas in a pure inductor, the voltage leads the current by 90 degrees like this. This is the current flowing, whereas the voltage across the inductor leads represented by VL by and it leads IR by 90 degrees. But this is a series circuit. When you apply the KVL for this, the resultant of VR and VL is the applied voltage. So then the vector will become like this. This is the applied voltage. So now onwards, when we say RL circuit VI relation means we can simply write the vector diagram like this. So current lags the voltage by some angle, but it's not 90 degrees because it's not a pure inductive circuit. It is a RL circuit. So look at this. So here we are taking only this and this. So this is V and this is I. I is common for both the elements and V is the applied voltage to the circuit. So the phase angle between this V and I is called the power factor angle, and cos of that will give the power factor of the circuit. Let us see a problem like this. Here find the equivalent inductance between terminals A and B. So look at this. Here we have a inductance L1 10 henries. Here we have the two inductors 2 Henry in parallel like this. So applying the rules for parallel inductors and series inductor, then we can write LAB, this between this and this, we write L1 plus 2 Henries in parallel with 2 Henries. Then we can write as L1 plus 1 Henry, because 2 into 2 divided by 2 plus 2 will give us 1 Henry, and L1 is already given as 10 Henry. Substitute that here, then 10 Henry plus 1 Henry, that is the net inductance between terminals A and B is 11 Henries. So let us take another problem based on capacitance. Here find out what is the capacitance between terminals A and B. And here C2 and C3, which are equal in magnitude but they are connected in parallel, and the whole circuit is connected in series with C1, that is 20 microfarads. So to get the capacitance between C and D, we write CCD is equal to C2 in parallel with C3, that is nothing but C2 plus C3, then we get 20 microfarads. Then redraw the circuit, that is we replace this with CCD, that is 20 microfarads, and here C1 is there like this. And now we calculate what is the inductance, or capacitance. CAB is nothing but C1 into CCD divided by C1 plus CCD. So once we calculate this, then we get 10 microfarads. So let us take another problem. So here is a resistor connected in series with two parallel inductors like this. So the impedance for this is we can calculate after calculating the impedance between C and C1, that is J2 into J2 divided by J2 plus J2, because two inductive reactances are given and we know their formula, so and their values are same, so we can write as XL divided by 2, that is J2 by 2, so we'll get here J1, or we can use this formula, then we get like this. So once we know this and we have the resistor here, so now we can say ZAB is equal to R plus ZL, so that is nothing but 10 plus J1. This is the total impedance of the circuit between terminals A and B. So let us see here, find the currents I1, I2 and the applied or supplied current I, and draw the vector diagram for the following circuit like this. Here the applied voltage is 200 volts AC supply and frequency is 50 Hz. And here this is the resistor R2 25 ohms connected in parallel with the R1, X1, which are connected in series like this. And let us assume the current flowing in the R1, X1 is I1, the current flowing in R2 is I2, and the current supplied by the voltage source is I. So because two branches are connected across the supply, so the current can be easily calculated as I1 is equal to V divided by R1 plus JX1. So because values are given, straight away we can put the values of voltage and the impedance, that is 200 by 10 plus J 25. Then after simplification we get 7.42 at an angle of 68.15 degree amperes. Then we also get I2 as V by R2. So 200 divided by R2 is 225. So we get 8 amperes. Then if we add this I1 and I2, then we get what is I. That is I is equal to I1 plus I2 vectorially. Then we get 7.42 at an angle of 68.15 degree plus 8 amperes. And if you represent that in the vector form, so because it is a parallel circuit, we take the voltage as a reference like this. And I2 is the current flowing in a pure resistor R2, so it is in phase with the applied voltage V. So then I1 will lag the voltage by some angle, but it's not 90 degrees because of the presence of the resistor, and that angle is here 68.15 degrees. So I1 lags V by 68.15 degrees. A resultant of this I1 and I2 will give us I like this. So this is the vector diagram or VI vector diagram for this problem. And let us memorize the voltage and current relations in a resistor, in an inductor, in a capacitor before we switch to the locus diagrams. In a pure resistor, when AC supply is connected, the voltage vector and the current vector are in phase in a pure resistor, whereas in a pure inductor, voltage leads the current by 90 degrees like this. Whereas in a pure capacitor, current leads the voltage by 90 degrees like this. So keeping this in view, we discuss the locus diagrams. So locus diagrams comes into picture when AC supply is available and if one of the variable or one of the passive element value changes with respect to time or with variation. So let us take simple R L circuit which is connected to AC supply and which has the variable inductor but fixed resistor like this. So here R1, L1 are connected in series with a voltage source, AC voltage source V1 and whose angular frequency is omega. And then the inductive reactance we represent as XL1 or XL or EX, that is given by omega L. And here L is variable, means automatically XL is variable, XL1 is variable. So to draw the locus diagram, this variation of the current with variation of the element in the circuit. So we take two extreme conditions of the variable element. So first step is assume the inductive reactance here XL1 is 0. So in that case draw the circuit. Then we get the circuit like this. R1 in series with a small 0 resistance wire connected to the supply. So it is as good as a pure resistor connected in series with a supply. In that case, the vector diagram for this is voltage and current are in phase with each other. So you can take as I as common, that is a reference. Then the voltage across the induct resistor is nothing but the applied voltage which is also in phase with the I. So we draw like this. I and V are in phase. And that VR is nothing but I into R1. The other extreme condition of the variable element, that is XL, is infinitum. When the inductance reactance becomes infinitum, then it becomes open circuit. Then the circuit will become like this. In that condition, the impedance will become Z is equal to R1 plus J XL1, that is equal to R1 plus J infinitum, that is infinitum. Then if you calculate the current flowing here, I is equal to V by Z, that is V by infinitum, that is 0 amperes. So we get 0 current. So that means, So with 0 XL value, we know the vector diagram. And with XL infinity, we know the current, that is 0. So taking this vector, so we can say this is the 0 current position. So this I is equal to 0 position. That happens only when XL is infinite. And this happens when XL is 0. So if the inductive reactance is more than 0 but less than infinity, then what happens? That becomes a semi-circle, and because it is a RL circuit, current lags always by 90 degrees, less than 90 degrees, and it will have the semicircle like this. So more less than XL means this value, this current. Similarly here, similarly here, similarly here. So reaches up to here. This is corresponding to XL is 0. So this is the locus diagram for fixed resistor and variable inductance. This simply shows the variation of the current with the variation of the XL. That is why it is called the locus diagram or current locus diagram for this circuit. Suppose we put the inductance fixed and resistor is variable and applied voltage is AC. So again we take the two extreme conditions of the variable element, that is resistor. If the resistor value becomes 0, then the circuit will become like this. So there is AC supply connected to a pure inductor because R is absent here. So in that case, as we have seen, the VI relation in an inductor is voltage leads the current by 90 degrees, that we can show like this. And the current flowing here is also maximum because the impedance is minimum, only XL is present. So that's the reason we write here I max is equal to V by X, and V leads by current by 90 degrees. This is one vector diagram with R is equal to 0. So what is the other extreme condition? R is equal to infinity. When becomes infinity, then the circuit will become open circuit like this. Then Z becomes R plus Jx, that is infinity, plus Jx, that is infinity. Then the current becomes I is equal to V by infinity, that is equal to 0 amperes. So then we can show this 0 point here. There is nothing but 0 current here. And when we show that on the locus diagram, we can show like this. This is the I minimum, that is 0, and this is the I maximum. And this I maximum happens when R is equal to 0, whereas here I minimum occurs when R is equal to infinity. In between, so here it is not a pure R or pure inductor. So it is a RL circuit. So for different values of R, the current lags the voltage by some angle but less than 90 degrees, not 90 degrees. So if the value is more than 0 but less than infinity, then the current phasor or the current locus will be semicircular like this in the first quadrant, that is like this. So for any value, look at this, V and I. It is I lags the V by some angle but less than 90 degrees. So let us take another circuit with variable inductor R1 and fixed capacitor C1 like this, connected to a AC source like this. So V is the AC voltage and its angular frequency is omega, and XC1 is the reactance of the capacitor, and R1 is the variable resistor. So to draw the locus diagram for this, take the extreme conditions of the variable element, that is when R1 is equal to 0, then Z value will become R1 minus JX1, and because R1 is 0, then we get minus JXC1. So in that condition, so the circuit will become like this. So it is a pure capacitor connected across AC supply, and we know the relation between V and I in a pure capacitor connected to AC supply, that is current leads the voltage by 90 degrees like this, assuming the vectors rotates always in the anti-clockwise direction. Here I is leading the voltage vector by 90 degrees. The V is lagging the I by 90 degrees. And this happens when R is 0. and the current flowing is maximum because the impedance is minimum. So that maximum current is nothing but V by XC1. And let us take another extreme condition of the variable element resistor R1 is equal to infinity. In that case, the impedance Z becomes Z max, that is equal to R1 minus JXC1. R1 is infinity minus JXC1 means infinity. So then the current is nothing but I minimum, that is equal to V by Z max, that is equal to V by infinity, that is 0 amperes. So having known this maximum current position, we can say this is the minimum position, and we can draw this same diagram here. And we say this position is R1 is equal to 0, that is maximum current, whereas here this is the R1 is equal to infinity, that is minimum current position. Whereas R1 value for less than infinity but more than 0, so there exists a circuit called RC circuit, physical values of R and C. In that case, current do not lead the voltage by 90 degrees but leads the voltage by some angle which is less than 90 degrees, like this. For any current you take it. So it follows what is called the semicircle, like this in the first quadrant, and that too on y-axis. So this is how we draw the locus diagram for RC circuit with R variable. Similarly, we can also draw the locus diagram with R fixed variable capacitor. Let us see here AC voltage connected to a variable capacitor with fixed resistor in series, like this. And the current taken by the circuit is small I. So let us take the extreme conditions of XC. Suppose XC is equal to 0, then that becomes a short circuit. Then the circuit will become like this. So then the impedance of the circuit will become only R, that is equal to, so the current that flows in the circuit will be maximum, that is I max is equal to V by R, and it is a pure resistive circuit connected to a AC supply. As we know the relation between voltage and current in a pure resistor, they are in phase with each other. So we can draw the vector diagram for this. XC is equal to 0 as like this. V is in phase with the current flowing to the resistor. So this is the condition when XC is 0. Suppose when XC is infinite, then the impedance will become infinite. So then the circuit will become like this. When the XC is infinite means that XC become open circuit, and only a resistor is there, and it's open circuit means no current flows. Or mathematically you can say I minimum is equal to V divided by Z. Z is infinity because X is infinity. So we get 0 current, no current flows here. So when no current flows but available voltage is available, so we have to show that in the locus diagram. We have seen already, this is the I position, this is the I maximum position. So same diagram we draw here like this, and this is corresponding to the XC is equal to 0 where I and V are in phase with each other. Now when XC is infinity, the current is 0, means this is I max, means this becomes automatically I is equal to 0. So for all practical values of capacitor, means more than 0 but less than infinity, current leads the voltage by some angle because of the presence of resistor. Otherwise, in a pure capacitor, current leads the voltage by 90 degrees. Due to the presence of this resistor, for all practical value of the capacitor, we find that the current varies in the semicircle form like this, but still leads the applied voltage by some angle like this. So that is in the first quadrant on x-axis. So far we have seen when only two elements are connected in series with AC supply, how to draw the locus diagram. Now we will see if two parallel branches are there and one of the element is varying and connected to the AC supply, how to draw the locus diagram. Let us say we have the AC supply here V, and here we have the fixed resistor R1 and fixed inductance reactance XL1. Similarly here we have the resistor R2 and reactance XL2. So but XL2 is variable with time. So now this R2 XL2 and this R1 XL1, they are in parallel with each other and they are in parallel with the supply V, and this V is AC supply and this V supplies current I, whereas the current taken by the R1 XL1 branch is I1 and the current taken by R2 XL2 is I2. So for this R1 XL1 we can say the impedance is Z1 is equal to R1 plus J XL1, and it is a fixed value because no variable element present, whereas Z2 means second branch impedance is Z2, that is R2 plus J XL2, but this XL2 going to vary with the time, and we know if R is fixed, L is variable connected to a single phase AC supply, and we also know the vector diagram when fixed or fixed L is connected to a AC source. So let us take first this first branch connected to the AC supply like this. So in that case we can say the current lags the voltage by some angle like this, that is V, and current flowing is I1 lags V by some angle. Because R is not 0, so definitely I will lag the voltage by some angle but less than 90 degrees. It's not 90 degrees. It's always less than 90 degrees. This is if only fixed elements are connected to AC supply like this R1, L1. Suppose RL circuit with XL variable connected to AC supply, what is the the locus diagram? This already we have seen. So when XL is variable, then the locus diagram will be like this. So here also current lags the voltage by some angle, but it is not 90 degrees because there is possibility of XL is equal to infinity. So like this. So it is a semicircle. Current always lags the voltage by some angle less than 90 degrees. And this is I2 and this is I1. So when we add these to this locus diagram and this vector diagram, that becomes the locus diagram for this circuit. So draw this as it is, that is like this V and I1. Now add this I2. So how to draw that I2? Just bring this I1 and draw like this. If you look at this V is in parallel to this line. This dotted line is nothing but V vector. So this is the vector diagram when two branches are connected in parallel, in that if one of the element is variable and connected to the AC supply. Suppose we take there is a RL branch connected in parallel with the AC supply, and also there is a RC element connected in parallel, but C is variable. In that case, what is the locus diagram? As usual, so RL circuit means current lags the voltage by some angle. We say the current drawn by this circuit by this branch is I1 like this, and I2 varies because this is XC is variable. So remember here current always leads the voltage by some angle but not 90 degrees because the presence of Xc variation from 0 to infinity. But at any time, so this branch current I2 will lead the voltage by some angle. So that is the reason we get like this. This dotted line indicates the vector position. So adding I1 and I2 will give us I at any point of time. So this is the resultant current I. For this is the resultant current. Similarly, like this. For different values, we get different I. Depending upon the I2, I will vary.